started. I would like to introduce Danielle Donkersloot, who is the Clean Water Program Director for the Isaac Walton League of America, and she is going to get our webinar started. Danielle?
Great. Thank you, Don. Thank you all for attending our webinar. And this webinar, we are pleased to present efforts from our U.S. Geological Survey partners. Ted Stetz is a research ecologist at the U.S. Geological Center, the National Research Program in Boulder, Colorado. Ted got his PhD from the University of Minnesota in ecology in 2017, and he's been working with U.S. Geological Survey since then. He is part of the NAWQA program. For those of you that don't know the acronyms, it's the National Water Quality Assessment Program, and it specifically looks at surface water trends and is the lead of the NAWQA Century of Trends project, which is part of a U.S. Geological Survey effort. Today, Ted is going to be talking about the corrosion, the corrosivity of water, and how the corrosion from our streams and rivers, sorry I'm stumbling, can make our water distribution systems can become a costly problem and can affect the human health on our communities on a wide scale. High chloride concentrations in water can travel through the pipes, for example, tap water traveling from the distribution system to your kitchen sink, and can increase the tendency of the water to corrode the pipes, which can lead to lead and copper getting into your tap water. So Ted's going to go over where the excess chloride comes from, how it gets into our waterways, and right now I'm going to turn it over to Ted. So thank you very much.
Thank you so much, Danielle. One correction, I got my PhD in 2007 from University of Minnesota, so I've been working at the USGS for about 10 years since then. I came out to Boulder directly afterwards. And so, as Danielle mentioned, I'll be talking today on the potential corrosivity of surface waters and U.S. rivers. And as Danielle also mentioned, this issue is important because of its links to water infrastructure as well as to drinking water quality. And the possibility of lead and copper contamination in drinking water. This work is an early product of the National Water Quality Assessment, or NAWQA, Surface Water Trends team. And I'll end the talk today with a short advertisement for the work that's going on there and where you can find some of our published data for potentially local things that you might be working on. Okay, so you've probably heard about cases of lead contamination in drinking water in the news. And the problems in Flint, Michigan really raised the profile of this issue, although I guess I would emphasize that it certainly didn't start there, and it's just something that we've become more, I think, alerted to since that situation. This map shows a few cities for which I was able to find news stories about drinking water contamination with lead, just doing a quick internet search, and these are just recent stories. And one of the stories actually reported that more than 200 drinking water facilities in New York and New Jersey were found to have elevated lead concentrations. In addition to these relatively high-profile cases, there's been more than 3,000 instances of elevated lead concentrations reported to the EPA since they started keeping track of this. So if I could make one point today, it would be that lead contamination of drinking water is something that typically occurs within the water distribution system. Okay, it's quite rare for water that enters the distribution system to have high lead concentrations. And so the lead is typically originates from within the system, and it originates from things like lead pipes, lead solder, and lead-bearing fixtures. And so the primary take-home message is that lead contamination is a corrosion problem. Corrosion mobilizes the lead in drinking water systems and can allow it to enter drinking water. The connection between corrosion and lead contamination is strong enough that controlling corrosion is really a major part of the lead and copper rule. And the lead and copper rule is the legislation that really sets the standards and practices for controlling lead and copper contamination of drinking water. So as part of the 1992 lead and copper rule, lead pipes are not used in new construction. But many older neighborhoods in big cities and in small towns have legacy lead pipes, either part of the city-owned distribution system or as part of the household plumbing. The drive to replace lead pipes is ongoing, but it can be a slow, expensive, and complicated process. One example I've heard recently is that for Pittsburgh, Pennsylvania, to replace all the lead service lines would require upwards of a decade of work and would cost up to $400 million. A similar assessment for Milwaukee, Wisconsin, found that it would be more than $500 million to replace the lead pipes there. So this is an ongoing process that is, slowly happening, and it's certainly not as prevalent in new construction, but it's something that is important in older neighborhoods and old construction. Additional complications arise when service line ownership is considered. Even when the city replaces its part of the service line, it's possible that there will be service line part of the service line that's owned by the homeowner, or plumbing that is within the household that contains lead as well. Okay, and so fixing that part of the problem is also slow and complicated, because you're really counting on the homeowner to realize that they have lead plumbing, to realize that it's a problem, and then to spend their own money to fix it. Okay, and so that can also slow things down quite a bit, and it presents a different kind of a problem than the cities upgrading their own distribution lines. And even when lead service lines are replaced, other factors can continue to contribute to the potential for lead to enter the tap water. The physical disturbance of actually replacing distribution lines can disrupt the scale layers on the insides of the pipes and potentially mobilize lead into the drinking water. Junctions where two different metals come into contact with each other can be a site where galvanic corrosion occurs, and I'll talk more about galvanic corrosion in a few minutes. Okay, so what are some of the things that make water corrosive? A lot of these factors are probably not that unexpected, but in many cases there's a sort of sweet spot that really minimizes corrosion. And one of the examples would be oxygen concentration. So very high oxygen concentrations can accelerate the corrosion of metals and cause them to become mobilized into the drinking water. But at the same time, very low oxygen can promote the growth of microorganisms that cause corrosion through other processes. So the goal is usually to keep oxygen concentrations at an acceptable range. Factors like alkalinity, pH, and hardness have a similar function, where at very low, for example, alkalinities, you can promote corrosion, but then sometimes at very high alkalinities, you can promote corrosion as well because of increased dissolved inorganic carbon concentrations, okay? And so really, these are like oxygen in the sense that there's usually a range that drinking water facilities will try to keep these at in order to minimize the corrosion. Higher temperatures cause corrosion rates to be faster, and this is actually one of the principal factors that guides corrosion rates within distribution systems. And then ion concentrations, in particular chloride and sulfate, can be important to corrosion because they cause the corrosion products to be more soluble within the water. Okay, and then finally, abrupt changes in water quality can also sometimes promote corrosion. So, part of the idea behind controlling corrosion is to have what's called a passivation layer, or the scale inside the pipes. And those form under different conditions, and they may be stable under the conditions under which they formed, but then if you change the conditions, you can disrupt those scale layers and potentially mobilize metals into the drinking water. So the steps to control corrosion are usually to try to keep many of the factors causing corrosion in a range that minimizes their corrosivity. So things like carbonation and decarbonation are used to control pH and alkalinity. Soda lime or caustic soda can be added to control pH, and in some cases to promote scale formation inside the pipes. And more recently, drinking water facilities have begun adding chemical corrosion inhibitors, things such as silicate and orthophosphate. Okay, now it may seem a bit odd that a drinking water facility would add phosphate when it's known to be such a problem for water quality at the other end at the wastewater treatment facility. But this is becoming more common, and the recommended dosages are quite high. They're in the range of 1 to 3 milligrams per liter of phosphate, okay? And I'll talk a little bit more about that later on as well. Okay, I'm going to move into more of the research associated with this. I wonder if there are any questions about this, the beginning part of this, or the motivation and background.
We have not received any yet, Ted, so you can keep going.
Okay, sounds good. So the USGS has some ongoing research looking at the potential corrosivity of source waters in the U.S. The first study published on this topic looked at the potential corrosivity of groundwater in the United States. This is important because private well owners are not subject to the same oversight as public water utilities. So the treatment for corrosivity and the testing for lead contamination is entirely up to the private well owner, okay? But groundwaters can be corrosive, and in fact, the study found that there was a high potential for groundwater to be corrosive in over half of the states in the U.S. The other study is going to be the major focus of the talk today, and it looks at surface waters, and in particular, how the potential corrosivity of surface waters has changed over time, as well as the seasonal and regional patterns in potential corrosivity. Okay, so now turning to really the main focus of this talk, we're using the output of a trend analysis to look at the implications for potential corrosivity in U.S. rivers. This work is part of a larger effort to describe trends in water quality throughout the United States, and the work is being conducted by the USGS NAWQA Surface Water Trends team. So we looked at trends in nutrients, pesticides, ecological communities, sediments, and along with that, major ions, okay? And major ion chemistry is an important factor in the potential corrosivity of surface waters, and chloride and sulfate are especially important to this issue. The NAWQA Surface Water Trends team has analyzed trends in chloride and sulfate from a number of stations across the country, and we can use this data to gain some insight into the changes in these ions and how it might relate to the potential corrosivity of surface waters. So this map is showing the spatial distribution of sites included in a chloride concentration trend analysis, and this covers the period 1992 to 2012. The triangles denote both the direction and the overall significance of the trends, with the black triangles showing places where we had highly significant either increases or decreases, the gray triangles showing places with less confident increases or decreases, and the open squares are showing places where we were not confident about reporting a trend for that particular location. The pie chart is displaying the results of the chloride trend analysis in a different way. The results are displayed by color, with the blue areas showing places with some evidence of chloride increases. The orange and yellow colors are showing places with some evidence of decreasing chloride, and the green showing places where we didn't have confidence reporting a trend either way. And so overall, we found that about half of the sites included in our analysis had some evidence of increasing chloride between the period 1992 to 2012. So chloride doesn't really stand out as an element that has really large wholesale trends across the entire United States. But when we look at the trends by land use type, we see something very different. In this case, we're looking at box plots of the change in chloride concentration between 1992 and 2012, broken out by land use. The land use categories are agricultural land use, mixed, so some urban and some agricultural development, undeveloped sites that are relatively pristine, and then urban sites. And we can see that the urban sites show a very strong tendency to have increasing chloride concentration. So what we're looking at are points above the line are showing places where we have increases in chloride, and points below the line are showing places where we have decreases in chloride. And the box plot of urban trends shows that those areas had very strongly increasing chloride concentrations between 1992 and 2012. So the sources of chloride to urban areas, I think, are relatively easy to understand, and they've been described in other studies. Road salt, especially in snow-dominated regions, can lead to elevated chloride concentrations in surface waters, at least locally. Point discharges can also be a significant source of chloride to surface waters, and these would include things like wastewater treatment facilities, industrial plants, and septic systems. And these two factors are the likely causes of the large increases in chloride in urban areas since 1992. So if we think about the linkages between chloride concentration and water quality, two main issues really stand out. And the first is that elevated chloride concentrations have adverse effects on aquatic organisms. Acute toxicity occurs at 230 milligrams per liter of chloride, and this level can actually be exceeded for periods of time in urban streams in snow-dominated areas. And as I mentioned before, elevated chloride concentration can also promote the corrosion of water infrastructure. And as we talked about earlier, corrosion is a ubiquitous problem for water infrastructure. It's been estimated to cost $36 billion annually nationwide. Corrosion in water distribution systems is also known to be important for human health, as we mentioned earlier, and metal contamination of drinking water can occur due to corrosion. So the potential for water to cause corrosion can be expressed using a few different indicators. For the purposes of this study, we'll focus on two of these. The first is called the chloride to sulfate mass ratio, and it's simply the ratio of chloride concentration to sulfate concentration. The second is called the Larson ratio, and it's the ratio of chloride plus sulfate to alkalinity. The chloride to sulfate mass ratio has been linked to lead and copper corrosion, and this has been shown in water distribution systems as well as in benchtop experiments, and it acts by promoting galvanic corrosion. Galvanic corrosion occurs when two dissimilar metals come into contact with each other, and this is most important in systems that have had partial lead service line replacement, as I mentioned a bit earlier, that in some cases you'll have the city replacing its portion of the water distribution system, and there is a point where there's a junction between the replaced pipe and the old lead pipe, and that junction can be a place where this galvanic corrosion can occur, and this is promoted by high chloride to sulfate mass ratios. It's probably more common these days, however, to find galvanic corrosion occurring in other situations such as where you have lead solder in contact with copper pipe, or when you have a fixture that contains lead, like a plumbing fixture that contains lead in contact with a copper pipe or something like that, okay? And so even though the lead service lines contain much more lead, it's probably more common to find lead in things like solder and fixtures these days. The Larson ratio, on the other hand, expresses the potential for water to cause corrosion of iron and steel. And just so you have a sense of the magnitude that's considered to be important for these indicators, a chloride to sulfate mass ratio greater than 0.5 is thought to promote corrosion. And when it gets above 2, it can actually be difficult to control corrosion using traditional means within a water distribution system. On the other hand, the corrosion of iron and steel can be promoted when the Larson ratio is above 1. Okay, so the Surface Water Trends team has the required data to perform trend analyses on major ions, and we can use the trend data to look for changes in water quality that might be related to potential corrosivity, and we can also assess the status of potential corrosivity in order to describe things like central tendencies, spatial patterns, and regional differences. And the main difference between a trend analysis and a status assessment is that a status assessment describes the conditions over a shorter period of time. And so the data requirements are not as stringent, and we gain a lot of sites and spatial coverage that way. And I'll be talking about both a trend assessment and a status assessment over the next couple of slides. Okay, so now we'll look at the trends in the chloride to sulfate mass ratio. The map and the pie chart are similar to what we saw for the chloride concentration trend analysis, but they focus on the chloride to sulfate mass ratio results instead. And in this case, approximately 2/3 of the sites included in the analysis showed some evidence for increasing chloride to sulfate mass ratio, as indicated by the blue colors. And similar to the chloride concentration trend analysis, we found that urban streams had very large increases in chloride to sulfate mass ratio between 1992 and 2012, while the other land use types had mostly small and inconsistent trends overall. Okay, and so this is very similar to the chloride concentration analysis where we're finding that urban areas are really changing most rapidly. And what we're seeing there are large increases in chloride as well as large increases in the chloride to sulfate mass ratio, which is known to cause the water to be potentially corrosive to water distribution systems. The status assessment covered the period 2010 to 2015 to give a better idea of the average chloride to sulfate mass ratio, and approximately 3 times as many sites were included in the status assessment. So as I mentioned earlier, the data requirements are not as stringent, and so we end up picking up a lot of sites and we can describe spatial distributions much better. And we can see that urban sites, in addition to having large increases over the past few decades, also have the highest average chloride to sulfate mass ratio. And also, if you remember from a few slides ago, a chloride to sulfate mass ratio less than 0.5 is associated with a low potential to cause corrosion. And above 2, it can actually be difficult to control corrosion through traditional means in water distribution systems. The urban areas from this study had mean and median chloride to sulfate mass ratios well above 2, indicating a high potential to cause corrosion. So the temporal records from individual sites can also show important seasonal differences in the chloride to sulfate mass ratio. And I'm displaying all of the chloride to sulfate mass ratio observations between 2010 and 2015 for 2 sites that were included in the status assessment. So months are indicated on the x-axis, the chloride to sulfate mass ratio is on the y-axis, and the individual points are showing individual observations by month over the status assessment period. The lines are showing a locally weighted regression that is meant to express the central tendencies of the observations. So first, if we look at the Connecticut River at Thompsonville on the left-hand side of the slide, we see that the chloride to sulfate mass ratio peaks during the winter months. And this is most likely due to the use of road salt as a road de-icer in that particular basin. There's a secondary peak that occurs late in summer, which can be explained in at least a few different ways, okay? So late summer in the Connecticut River is a very low flow time of the year. And so the water that is in the stream at that time is dominated mostly by either groundwater or by water that is coming out of wastewater treatment facilities, okay? And so it could be that the wastewater treatment facilities have a relatively high chloride to sulfate mass ratio and are influencing the chloride to sulfate mass ratio at that time of the year. It can also be the case that because of the prolonged use of road salt in that particular basin, that you're actually getting a contamination of groundwater with road salt. And this has been demonstrated in a few areas in the northern parts of the country that have had a long-term usage of road salt, okay? But in any case, the pattern that we see in the Connecticut River is consistent with the idea that road salt really drives these high winter values. And the second thing I'll point out about this is that all of the values in the Connecticut River are quite high. As I mentioned before, when the chloride to sulfate mass ratio is above 2, it indicates really a high potential to cause corrosion in a water distribution system, and the majority of the observations are above 2 in this particular basin. Now, if we look at the right-hand side of the stream, the right-hand side of the slide, we're looking at the Platte River from Louisville, Nebraska, which is in a much different kind of situation than the Connecticut River at Thompsonville. And the first thing we'll notice is that the chloride to sulfate mass ratios overall are much lower in the Platte River at Louisville, Nebraska, okay? And they're, for the most part, not above 2, and many of the observations are actually below the 0.5 limit where the chloride to sulfate mass ratio could promote corrosion at all. But one thing we do see is that in late summer, there is a collection of very high observations with chloride to sulfate mass ratios well above 2, okay? These particular observations coincided with the very severe drought in 2012. And so in this case, they seem to be related to a hydrologic event rather than to the use of road salt, as we saw in the Connecticut River, okay? So the Platte River is really showing us something different. We're seeing a different process that's leading to potential corrosivity in the surface waters, and we're seeing a difference in the timing and a difference in the regularity of something like this, okay? And, if we could put more slides up here of more different sites, and each of them would really tell their own story. And I think this really goes to the point that monitoring for chloride to sulfate mass ratio is going to be important to optimizing corrosion control in water distribution systems. Okay, so now I'll talk about one additional analysis included in this study. And this one was looking at the linkages between surface water quality and the occurrence of a lead action level exceedance at a drinking water facility. So an action level exceedance is a violation of the lead and copper rule by a drinking water facility. And it's defined as a situation when the 90th percentile of tap water samples is above 15 parts per billion in lead concentration. So in other words, more than 10% of the samples taken from tap water in a distribution system were above the 15 part per billion limit. Okay? And when this occurs, drinking water facilities are supposed to report this to the EPA, and it's entered into a database called the Safe Drinking Water Information System. So our approach was to define watershed boundaries for all of the trend locations, and I have the trend location marked out as a black triangle on this particular schematic. We then located all of the surface drinking water intakes upstream of the sampling location, and we counted the total number of lead action level exceedances in the basin. Okay, so the number of times when it was reported that there was an elevated lead concentration in the tap water. We then related the number of exceedances to the water quality at the monitoring location, and look for relationships that way. Okay, the basins included in the study were required to have at least 5 intakes, and the basins were also limited to be 30,000 square kilometers or less in size. Okay, and the reason we wanted relatively small basins is we wanted some way of looking at the water quality at the monitoring location and having some confidence that it would actually reflect the water quality at the intakes, surface water intakes. Okay, so we looked at the number of action level exceedances compared to chloride concentration, Larson ratio, and the chloride to sulfate mass ratio. And here we're looking at the site average chloride to sulfate mass ratio on the x-axis versus the number of action level exceedances on the y-axis. Okay, and it's pretty messy, but there is a tendency to have a greater number of exceedances at high chloride to sulfate mass ratio. One thing that makes the figure really difficult to look at and to analyze statistically is the number of sites that had 0 action level exceedances. Okay, and the presence of these occurrences make the data difficult to analyze using traditional means. So instead, we used a logistic regression to ask about the probability of there being at least 1 action level exceedance per 10 drinking water intakes in the basin. The data have a lot of scatter, but we did find a statistically significant relationship such that places that had higher chloride to sulfate mass ratio did have a higher probability of having a lead action level exceedance. Okay, there is a lot of uncertainty around this relationship, and that's really to be expected because we didn't do anything in terms of looking at the size of the water distribution systems or looking at the kinds of corrosion control that was in place in these. And I guess strongly advocate that is some follow-up work that needs to happen. So nevertheless, this is important for a few different reasons. So first of all, it does link lead action level exceedances to surface water quality. And the studies to date have really just looked at the quality of finished waters within the distribution system. So in other words, they looked at the chloride to sulfate mass ratio after all of the water treatment had taken place. Okay, but this links it back to actually the surface waters at these locations and the probability of finding a lead action level exceedance. Okay, so just to recap the major findings of this study, there were large increases in chloride and chloride to sulfate mass ratio, particularly in urban areas. In addition to the long-term changes in potential corrosivity, there were important seasonal patterns described by the data as well. And I only went over 2 of these, but there are actually quite a few more different kinds of patterns that we observed in the data. And we also found a statistical relationship between the potential corrosivity of surface water and the probability of a lead action level exceedance at the tap.
Ted, can we, are you nearing the end? We have a couple questions that have come in.
We can go through the questions now, and then I'll wrap up.
Okay, great. So the one question we have here is if chloride sulfate ratio is a strong indicator of corrosivity. Sorry, that word's going to tongue tie me the whole time. Then why isn't sulfate one of the corrosion inhibitors water purveyors use?
Yeah, that's a good question. I think the idea is that the phosphate is much more effective, and the reason the phosphate is more effective is that it creates a passivation layer on the inside of the pipe, and it's a relatively stable passivation layer. And so lead phosphate is a pretty stable compound, and it will stay on the insides of the pipes. That said, drinking water facilities do add sulfate to drinking water, but they don't do it for corrosion inhibition. They add it in the form of alum, so aluminum sulfate, and they add it as a coagulant. And some of the instances of lead contamination relating back to the chloride to sulfate mass ratio resulted from a change in the coagulant from alum to a chloride-based or aluminum-based coagulant that changed the chloride to sulfate mass ratio. And so, there is evidence that within these drinking water facilities that changing the chloride to sulfate mass ratio through a difference in the treatment wound up affecting the mobilization of lead within the distribution system. But I agree, that is a good question of why you don't add sulfate to drinking water facilities. And I'll just point out the other thing is that this is not, there is some disagreement in the literature about this, and there is some thinking that high concentrations, the chloride to sulfate mass ratio by itself is important, but high concentrations of one or both can also be corrosive to water distribution systems, as I mentioned before, in the Larson ratio. And so it would potentially cause some other issues as well.
Okay, great. And just one more, and then we could hold the rest till the end. We're getting some in now, which is great. So the other one that I have here is, as with groundwater, you can see the effects of geology upon the chloride sulfate mass ratio. How does this compare to what the anthropogenic effects regionally across the country?
Yeah, that's a great question. I mean, you can't get away from the geology. The difference, I would say, is that if you're in a setting where the water has always been corrosive, right, you probably have been dealing with this for a long time, and you've figured out how to handle the problem. I live in a place, Boulder, Colorado, that does add phosphate to its drinking water because we are in the drinking water that we get here is very dilute. It comes from the mountains, and it comes in relatively corrosive. And so this is something that they figured out, I think, a long time ago, is how to deal with this. What's different are the places that maybe formerly were not as corrosive, but over time, as we've been adding more road salt, and especially when we get these spikes in salt in the wintertime, and you can see a lot of these spikes, there'll be a snowstorm in the wintertime, the salt goes down, and then as soon as it warms up, you get this huge spike of chloride or specific conductants within streams. Okay, this is something you can see. And so in those cases, these are kind of intermittent events that maybe the distribution system is not set up to deal with in that case. In terms of how variable these things are, I didn't put the slide up there, but it's quite remarkable that there are undeveloped locations in the United States that have very high chloride concentrations that I assume nobody lives there because the water is not as good. And some of the most urban sites in our study had chloride concentrations that were similar to these undeveloped locations. And so I think we have pushed the anthropogenic component of this far enough that we're equaling the geology in some places. But having said that, the geology is the overall driver, and you are absolutely correct about that.
Okay, great. Let me give you one more because we're getting quite a few in, and then I'll table the rest of the questions to the end. So the other one is, has the quantity of salts been applied to roads increased during the time period considered in the study?
Yes.
Okay. All right. Let's continue, Ted.
Sure.
Great.
So I'm almost done here. So I just want to go over some of the implications of this. I mean, it's important, I think, to state the problem correctly, because there are many places where, as I mentioned before, water distribution systems have been dealing with corrosive water for a long time, and they really have it dialed in, and they're doing an excellent job with this. That said, we did find that, first of all, the conditions are changing in many places, and they can be a bit unpredictable in terms of these winter storms like I just described and things like that. And so really monitoring of these critical elements will be needed to optimize corrosion control. And so if you're looking to control corrosion within your distribution system, you have to have proper knowledge of what the corrosivity is in your particular watershed. The trends that we described suggest that potential corrosivity could become worse in certain areas over time. We found a very large increase in chloride concentrations and chloride to sulfate mass ratios in urban areas over our time period. If this were to continue, it suggests that potential corrosivity would get much worse in many places. The effects of this would be a requirement to increase corrosion control over time. And as I mentioned before, many places are turning to orthophosphate inputs as a way of controlling corrosion. This puts an additional burden on wastewater treatment facilities, and you also have instances where untreated water would get into waterways. You know, for example, if you're watering a golf course or your lawn or something like this, this can all end up in the surface water as untreated water that would have high phosphorus concentrations. And so over time, you know, you could be undoing some of our work to really reduce phosphorus concentrations in surface waters throughout the country, okay? And just as an example of this, in Britain, it was recently discovered that 95% of drinking water facilities there are using orthophosphate as a corrosion inhibitor. And so, you know, there is a possibility that we would see something similar here in the future. I didn't talk a lot about this, but in some cases, zinc is added along with orthophosphate to also help with corrosion control. And you can see, for example, downstream of wastewater treatment plants that use zinc, you can see much higher zinc concentrations in the water. Zinc is not particularly toxic to humans, but it is toxic to aquatic invertebrates and to fish populations. And so you could have an environmental effect that way as well. Okay, and I'm just going to end really quick with an advertisement for the NAWQA Surface Water Trends team. So as I mentioned before, we were looking at trends in surface water, nutrient, pesticide, sediment, carbon, salinity, fish, invertebrate, and algae over time. The chemical constituents, we are looking at trends in concentration as well as trends in fluxes. We have we looked at trends over 4 different time periods going back to 1972 to look at the overall effects since the Clean Water Act passage, and then also over shorter time periods to look at more recent trends. The data sources for this analysis came from the USGS NWIS dataset, the EPA STORET, and then lots of other state, local, and federal databases. And overall, we had 185 million water quality records from 480,000 sites, although we pared these down pretty quickly when we started doing our quality control and things like this. The results are all available online, looking at this online trend mapper, and here's the website that goes along with that. So you can find trends for different time periods and different constituents, and you can click on individual sites and download the data for that particular site, and as well as the trend model output. And I'll just end on this. These are additional resources. All of the work I've described today is published. The data are available, and there's a lot more information on the methods and the interpretation that went along with that as well. That's all I had for today.
Okay, great. So we have a flurry of questions, which is great. If anybody has raised their hand to speak, please type it into the questions down below. Everybody is muted so that we could just roll through these questions pretty quickly. If we don't get to your question on this webinar, then we will follow up independently with you. So just rolling through some of these now, Ted, we have, is there any research being done in conjunction with U.S. Geological Survey's environmental health mission area?
Not that I'm aware of, although the USGS is a very large organization, and I'd hate to speak.
Sure.
I am not involved with anything, and I'm not aware of anything. But that's a good question. This would be a good place for them to step in. I agree.
Okay, good. The other one is, would you expect similar chloride-related corrosion effects in lead distribution systems for groundwater supplies?
Yes.
Yes.
I would.
Okay. Let's keep going here. What are promising options for reducing road salt use?
Yeah, this is a great question. You know, these range from the improbable futuristic to very mundane. The things that seem to work the best right now are best management practices for salt application and applying salt in different ways and in different times that minimizes your need to use road salt. Beyond that, you start talking into some really futuristic things. The other options, you know, there's some sort of organic-based de-icers that people will use in the wintertime. These all have their own environmental issues as well. Organically based de-icers also end up in surface waters and can cause a BOD problem there. You know, there's a move towards using, instead of sodium chloride, using magnesium chloride. That doesn't really solve the chloride problem, and it creates an additional magnesium source. So there's not really a lot of good options. There are places where they have installed heated roads and things like this. You know, who knows? Maybe we'll get there someday. But in the meantime, it's really best management practices to minimize road salt usage is really the direction that I hear people going.
Okay, great. Since each region is unique in its trends, how should management plans be approached?
Yeah, I mean, this goes back to the need for monitoring and the need for recognizing that there are different issues in different places. The story, the way I've told it here today, really focuses on the road salt issue because it is so obvious in the data. There are other places where you would be wise to think more about changes in temperature because temperature also affects corrosion rates, okay? And so I think the first step is really to understand the problem and to understand the differences regionally and then develop a management plan based on what the problem is for that particular region.
Okay, great. Another one that's come in is, would landscapes that include heavy amounts of agriculture and orthophosphate source potentially mask the impacts or possibly reduce it?
That's a good question. I hadn't thought of it that way. It strikes me that you know, the dosages required within a drinking water facility are in the milligram range, and it's not often that you find, even in polluted waters, it's not often that you'll find milligram per liter concentrations of orthophosphate. In many places, the target concentration for orthophosphate is 0.05 milligrams per liter. And so even in a relatively compromised watershed, I don't think you'd be reaching a high enough concentration to do that. And the other thing is it's possible it would be taken out during some of the early steps of the treatment process for drinking water as well.
Okay. Let's go through more questions. Was the chloride to sulfate mass ratio lower in states that have adopted chloride criteria?
I don't know. That's a good question. I'm going to write that one down.
Okay. Yeah, the question that keeps coming up is, would it be possible for us to get your slides, just so everybody knows here that the webinar is recorded and will be available You should get a link for it, and we will also hang it up on our YouTube channel. Let's keep going here. Is there any evidence that trends in sulfate concentrations may be affecting the, oh, this is the ratio that it looks like chloride SO4 ratio?
Yeah, that's a really great question. The short answer is no. There are places where this is important, and so I tend to think on a national scale. And so on a national scale, the answer is no. But there are individual places where this is important, and that's a really good question. And I have to say, coming into this study, I was expecting to find more of an effect of the sulfate trends because they're undeniable in many places. There are very strong trends in sulfate. But if you do download the paper and look at it that goes along with this, we talk a lot about that and the fact that the increases in chloride to sulfate mass ratio are very strongly related to changes in chloride rather than sulfate. And I got to say, I was very surprised by that result as well.
Okay. What are the health or other consequences of corrosion of iron and steel pipes?
Yeah, that's a great question. There's a lot of, there's a condition called red water, which our EPA co-authors spend a lot of time dealing with. And this is a problem of corrosion of iron due to increased Larsen ratio. I don't know that that has a direct human health effect by itself. That said, a pipe made of iron or steel has a lot of other elements in it as well. And if it is dissolving and corroding, it's likely that you're getting corrosion of some other metals that you probably don't want to have in your drinking water.
This is a question that I was going to ask too. So a couple of us are on the same page here. What types of monitoring would you suggest that volunteer monitoring organizations could engage in? There are, as you know, there are citizen scientists and volunteers around the nation, and honing in on what some of those parameters may be for us to consider would be helpful.
Yeah, that's a really good question. I'm going to assume that most citizen science monitoring efforts don't have the ability to run, for example, an ion chromatograph or something like this. And that's what you would need to look at, for example, chloride or sulfate in surface waters. But what you can do is you can develop, for an individual site where you're working, over time you can develop a relationship between, especially if you live in a place where road salt is being used, you can develop a relationship between chloride and conductivity. And then I guess I would recommend looking at conductivity over time, because that is something you probably have access to. Most drinking water facilities will look at conductivity, although they are not necessarily required to look at chloride and sulfate individually. But if you had that relationship and you could really nail this down for your site, it would be very useful information to know what the specific conductance is and what sort of seasonal or storm-related features might be present in your particular watershed.
Great. Thank you. So, is there any research on how road salts flush out of streams or superficial aquifers?
Yeah, there's some really excellent work on this. I'm drawing a blank on the author's name. I believe she's in either Syracuse or Buffalo, New York. We cite some of her work in our paper.
Okay.
But there is work on this, and that's what some of this is what I was referring to when I talked about evidence that groundwater has been contaminated with road salt in urbanized areas, and some of it is her work. It's really top-notch work. It's great.
Okay, great.
Hey, Danielle, I had one that came to me via the chat box, if I could jump in with this.
Sure.
For the chloride sulfate mass ratio, I think that's what CSMR is, how important is a decline in sulfate deposition from the decline in SO2 emissions from coal-burning power plants versus CI or increase from road salt?
Yep. Yeah, that was a similar question asked a few minutes ago, and the answer I gave then is that there are places where this seems to be important, and this is really, if it's a local issue, it's important to understand whether it's from an increase in road salt or from a decrease in sulfate. From a national perspective, in terms of doing the statistics nationally, it did not really show up as being all that important. And again, I was surprised by that, and I was expecting to see more of an effect of decreasing sulfate overall, but I didn't really find that. It was really more the chloride increases that were driving this. And nationally, right? But locally, it might be a different story, and it would be important to know that.
Right. So just one of our volunteer coordinators out there responded to the volunteer question just as an FYI. Chloride, Quanta, Tab, strips done by NAWQA are easily accessible technology for the volunteer monitoring citizen science applications. So thank you for that. We have a list of questions here. We'll do a few more, and then we might have to answer some of these offline. How about water softeners and their contribution to adding salt into the environment? Has that been looked at?
No, not that I'm aware of.
Okay. All
That's
right.
a good no.
Yeah. Is there anything that can be added that will bind and precipitate out chloride?
Not that I'm aware of. And again, this is a problem. The chloride concentrations in surface waters and the source waters, as they come into the drinking water facility, there's not really a good way to precipitate out chloride. And so the chloride concentrations tend to be more conservative throughout the process. You can always add chloride, which does happen, like I mentioned before, with some of the coagulants that are used and things like this. But taking it out is quite difficult. Sulfates can be precipitated much easier than chloride, but chloride's fairly conservative, and it is a difficult thing to precipitate out.
Okay. Here's a question here. What do we tell homeowners that are concerned about potential lead in their drinking water? Is there a particular agency that would test their home? So, I guess it's just going to that, starting that discussion within your community, and then the what to do about it.
Yeah, that's a really good question. This is pretty far outside of my area of expertise.
Sure.
I mean,
no worry. Yeah.
I would recommend going to your local water provider first of all. Beyond that, I'm drawing a blank, and it's not my area of expertise. I hate to give some of the wrong information.
That's okay. Let's just see here. Gosh, we might have to take some of these offline because there's a lot. Is the orthophosphate chemically bound while it controls corrosion? In other words, does it wind up in the scale on the pipes, or does it pass through the system in the original concentration?
The answer is yes to both of those. So it does end up as scale on the inside of the pipe, and that's the reason it's added in the first place.
Okay.
And that adds to this what's called the passivation layer. So those are the sort of inactive layer on the inside of the pipes that protects them from being corroded. But in order to keep that in place, you need to have a relatively high phosphorus concentration, otherwise it'll begin to dissolve, right? And so that's where the recommendation comes from, to keep the phosphate concentrations within the distribution system in this 1 to 3 milligram range. And those recommendations are system-wide, okay? And so from the distribution system to the very end of the, from the drinking water facility to the very end of the distribution system, that last, pipe at the very end of the distribution system is supposed to have 1 to 3 milligrams per liter of phosphate. And so even after you account for all of the consumption that's happening, or the passivation that's happening within the system, you're supposed to keep that concentration at 1 to 3 milligrams per liter all the way downstream, the most distal part of the distribution system.
Great. Let me go through here. Oh, we had another response come in. regarding home testing. So there's two. Oh, I see three. I know who you are. From the same person, but very helpful here. So per EPA website, you could buy lead testing kits in home improvement stores to collect samples and send them off to laboratory for analysis. EPA does recommend sending samples to a certified laboratory for analysis, and a list can be made available from state or local drinking water authorities. And then there is also a hotline. So you can Google that. Thank you, Barbara. You can Google that for that hotline. Look around the EPA website. Let's see. Trying to be selective of my questions. Does the chloride sulfate mass ratio still apply with using phosphate inhibitors?
I'm not really sure. I think that the phosphate inhibitors are supposed to work even in high chloride to sulfate mass ratios. But that said, there could be a point at which they are just not effective. My understanding is it's a fairly complicated question, but the phosphate inhibitors are much more effective, and in many cases they will create a passivation layer even in the presence of high chloride to sulfate mass ratios.
Okay. There's a question here about what about microbial-induced corrosion of concrete-lined sewers?
Yeah, I mean, that's a good question. That wouldn't be in your drinking water necessarily. So that would be something that would end up, the concrete-lined sewers that would end up in the streams. And there is some evidence from urban studies that you have increasing calcium and alkalinity and magnesium in urban areas. And some of that could be due to corrosion of cement pipes and things like this.
Great. And let me just make sure that I have one more comment here from our folks that may be helpful for this discussion too, on the way of the regulation side. In case this helps, EPA writes the regulation for lead and pipe for public water systems. Most states have enforcement authority for LCR, starting with calling your water system is the best starting point. So with that, I think we have gone through the questions. I am happy that this has been a lively discussion. If there are any other questions that have come in or points that we have not captured, be sure to share them with Ted. But at this point, I am going to stop answering the questions. I don't know, Ted, if you have any other thoughts that you want to put out there, or?
No, other than I'm happy to keep answering questions to this topic. I mean, maybe not right at this moment, but if people have them and want to send them to me, I'm happy to continue the discussion.
Yeah, great, thanks. Some of them, was there a particular reason why you looked at the mass ratio and not the molar ratio, for example, was one that has come in?
Yeah, I mean, we were using sort of the accepted sort of literature values on this, and things are typically reported as mass ratios rather than molar ratios. I mean, you would end up finding the same thing, but you would just have a different scale that you're working with. The Larson ratio that I presented a little bit earlier, I didn't really end up talking about it that much, but those are in equivalent ratios, and so that would be closer to, not exactly, but it would be more like a molar ratio than a mass ratio. But the chloride to sulfate mass ratio is sort of an accepted within the drinking water community a way of looking at the corrosivity, and so we stuck with that convention.
Great. Thank you. Well, at this point, I'm going to, Ted and I will get back to you with some questions that we may not have had a chance to answer. I want to thank everybody for staying on the call till the end. I'd like to thank Ted for sharing his expertise and what he has learned with this important issue. I think based on the questions, people are interested in finding out more about this, and thank you to all that are interested in water monitoring and out there protecting our rivers and streams and being the voice for those rivers and streams. So thank you so much. We're going to end.
Thank you.